welcome to today's event, technical meeting for SEI Philadelphia, evaluation of ASR affected components and rehab of the Varina Enon Bridge. Just want to go over some housekeeping for SEI Philly before we hand the presentation over. First, as the email indicated, this meeting is being recorded, and since this is a town hall, your microphone and camera has been disabled. But to ask questions, we do have the QA function available, so please use the QA function during the presentation. If you have any questions, feel free to do it during the actual presentation, and at the end, we will answer the questions for you. And then obviously during the Q&A period, feel free to keep adding to them. If you want to stay up to date with SEI Philly, we have our website right there, seiphilly.org. You can always send us an email at phillysei@gmail.com. And if you have your phone, grab it real quick, take a picture of that QR code, and that'll take us to our LinkedIn page where you can follow us. That's a good source to get information of our upcoming events and anything else. SEI Philly. Just want to recognize the 25-26 board members here. My name is Mike Urban. I'm the chair, and our vice chair is Colin, treasurer Greg, secretary is Alex, our program director is Nathan, director of public relations Justin, Kylie's our deputy director of public relations, and our past chair is Keith Merrill. Wanted to thank everybody for sponsoring the 25 SEI golf outing. Baker, HNTB, ACOM, BDI, Pannoni, Keller, Morshea, HDR, and SAI. And as I said last meeting, we do have the next, in May 15th is our next event. So going into that, here is the QR code. So again, keep those phones out, grab a picture of that QR code. That will take you to the registration form. I'd love to see everybody there. It is going to be May 15th at Kimberton Golf Club in Chester County, 8 a.m. registration, 9 a.m. shotgun start. And as always, there will be food there. There will be beverages. There will be prizes. There will definitely be fun, and you do get to meet new people. So come on out, have fun. It's a great day at the course. No prior experience at golfing is required. None of us are good, because if we were good, we wouldn't be engineers. So enjoy, have fun, come on out, and get to meet some other structural engineers. In addition to our golf event, we do have our ASCE multi-tech session on April 14th. That's at the Inn at Swarthmore. We'll have a brief, session before with dinner, and then SEI, DBGI, and T&D will have their breakout sessions. We'll be obviously hosting the SEI breakout session, which will be Ronnie Madluck from High Steel on bridge fabrication. So that'll be a great presentation for us. Then May 14th at McCormick Taylor's office, we will be hosting the City of Philadelphia for the Schuylkill River Trail Bridge, not necessarily about the design, but more so the management and the construction side. So I think that's going to be a great presentation, for the city and for us to be able to be a part of that. And then, as I mentioned, May 15th, the golf outing. And then that would wrap up our 25-26 year. So stay tuned for 26-27 calendar events. And as always, if you have anything that you would like to present or you're passionate about, send us an email and we will get you on next year's calendar of events. As you probably know, as I mentioned before, we did receive a $500 grant for the SEI Futures Fund, and this year we put it towards MOLA kits at our student event, which was held on Tuesday, and it was at Villanova. So a part of that student event was doing a panel discussion. We had some great panelists. One, unfortunately, it was not able to attend because her car was broken into, but we still pushed through, and we had a great event hosted. It was emceed by our vice chair, Colin Drager, so that was great. And right there, you can see the students working with that MOLA kit. I don't know if you're familiar with MOLA kits, but it's essentially a structural analysis a visual aspect of structural analysis where you can see pin connections, fixed connections, and you can build structure. So it was good that they were able to see, everything that they're learning in college in real life. So for today's speakers, we have Marisol Sui Chang and we have Nick Nicholson here. Marisol's from BDI and Nick is from Parsons. So at this point, I will turn it over to them and for their presentation. Looking forward to it. And I think Nick, if you wanted to share, I can put your screen on.
Let me get the mic.
Okay, I hear you.
Now you can hear me.
Yes. There we go. All right, I see it. Perfect. All right, floor is yours. Thank you.
Well, thanks for the opportunity. Appreciate talking about this project. It's a very interesting, challenging project, and Marisol and I will hope to keep those interests going. We're talking about the Varina Enon Bridge, and our presentation today will focus on 3 areas and then give it time for questions from you all and let you know status update of where we are going forward. Overview of the structure itself. It's Virginia's first and only cable-stayed bridge. It carries I-295 over the James River, right at the borderline of Chesterfield and Henrico County, which is it's a bypass, a circular of the city of Richmond. Originally completed in the early 1990s. It has a center main span of 630 feet with approach spans of 150 each. Post-tension box girders and piers with a cast-in-place pile cap. That's where our real problem exists, is in the cast-in-place units of the structure, as they were found to have ASR contamination. Basically, through our regular biannual inspections, we're starting to notice distress in multiple units of the pile caps. And as it continued to deteriorate due to that ASR expansion, concern was then given to its ability to carry the loads. Aesthetically pleasing bridge if you ever been on it, but the problems lie down in both the exposed and buried pile caps, as you'll see as we get further on. Here is the profile and some of the representative piers of the structure. Note again that we had post-tensioning of the pier caps. Basically up over the James River. These are 2 dual bridges with some 27 pairs of piers. This particular presentation focuses on the northern approach, because through inspection, testing, we found out that those were mostly in the severe deteriorated conditions. We came along after a study conducted by WSP. Our study was in the 2018 timeframe. Ours was in latter years of, I'd say the mid years of 2023. We basically advised VDOT, the owner of the bridge, that the footings were in a state of severe cracking, and the load carrying capacity was at risk. VDOT did an initial study to consider the replacing of the structure versus rehabilitation. Just to step back, ASR, alkali-silica reaction, is normally a cancer of concrete. There's not a remedy thus far, despite research that has been conducted by the University of Texas at Austin, Federal Highways, and other owner agencies have just determined that mostly when it's there, you replace the concrete, you replace the components, you replace the structural elements that have the reaction. We did not have that benefit or luxury with the Varina Enon Bridge, being that it was the pile caps for the footings. The replacement means we replaced the bridge. And at an initial estimate of over $1 billion, okay, what happened here? Sorry about that. Of over $1 billion, VDOT decided to extend the life and come up with a solution that would provide for extending the life at least 25, preferably 50 plus years, in order so it could plan and program the additional replacement if needed. Marisol, you want to jump in?
Yep. Thank you, Nick. So now we'll go over some of the project history and some initial investigations. So like Nick said, the Parsons team recommended a prioritized approach, first to look at the moderate and severe cracked pile caps based on some of the core samples taken from the initial investigation, some photography, material testing, that kind of stuff. They did recommend that at least the severely cracked pile caps in the north approach be given the highest priority, or then again, like the goal would be to extend the life by doing some sort of repair. And in this case, the schematic encapsulation system was studied and recommended for the implementation as a long-term solution. So like Nick mentioned, there was during regular inspections, extensive map cracking of these pile caps, as you can see on the photo on the right, were observed. From that, some of limited material testing from WC and others in previous years included petrographic analysis, chloride testing, compressive, split tensile, modules of the system, and then some residual ASR expansion testing. Next slide, please. From these results, some of the valuable information obtained was that, in fact, they did have alkali-silica reaction in the concrete. They also had some high near-surface chloride contents, and in general, worse visual distress and mechanical properties of the north approach pile caps, which is why Parsons, in this case, recommended to start over there and perform sort of repair encapsulation. Next slide, please. So taking a step back, what is ASR? I think Nick started off really well by saying that it is considered the cancer of concrete. But ASR in concrete is a chemical reaction between the alkalis in the cement paste and the reactive silica in the aggregates in combination with moisture that produce an expansive gel that can cause cracking and deterioration over time. So this expansive gel, this reaction generally, because it does involve the aggregates, it can start within the aggregate and around the aggregate. So it starts cracking inside the aggregates themselves and then starts expanding. So a lot of the times ASR can be manifested sort of like the map cracking that you see on the photo on the left. But also if you take a core and you take it and it's pretty severe ASR, then you can see how the aggregates themselves, you can see the cracking in and around the aggregates with a little bit of a whitish material. So that's one of the ways to sort of preliminarily deduce that ASR is occurring. But at the same time, you do need essentially petrographic examination to be able to confirm that it is in fact ASR. So from the preliminary investigation, the owner still needed to answer a lot of questions to allow for effective decision making and design of the repairs. These were, why are the north approach piers in worse condition? What's the difference between the north and the south? How has the concrete already been impacted, right? So where are we in point of time in this, cancer? What is the potential future expansion from ASR? What specific piers need to be prioritized? And then what other deterioration mechanisms are present? Because this is an extensive list, we're only really going to prioritize what is the potential future expansion for ASR for the current investigation, because that was one of the main questions that would inform the repair design. So we'll focus on that next. So many ways. Alrighty, so for the current investigation, for testing and project goals, again, we wanted to determine key information to confirm design assumptions and inform an effective repair design that Nick will go on after this section. Key information included in situ mechanical properties, making sure that the assumptions on these mechanical properties were correct, and if not, course correct for that. This included compressive strength, split tensile strength, stiffness damage testing, and modulus of elasticity. We also wanted to look at the remaining ASR expansion based on advanced models using the damage rate index, ASR expansion testing, and residual alkalis. And these advanced models were performed by Dr. Leandro Sanchez from University of Ottawa. So he was one of the subject matter experts for the project. So the testing performed, again, we did a lot of testing for this investigation of the north approach. We did some non-destructive evaluation, high-resolution imaging, and ultrasonic surface waves. We also did some petrographic testing to look for the types of aggregates and constituents, hardened area testing, secondary deposit or DEF, and ASR damage rate index or DRI. For the mechanical properties, we did compressive strength, split tensile testing with modulus of elasticity. For the ASR testing, we did residual alkali expansion testing and water-soluble alkalis. And for the chloride testing, we also did acid-soluble and water-soluble. And again, we're not going to go over all of these because it's a very in-depth investigation. We'll only go over primarily the ones that are bold in the screen.
Marisol, can I interrupt for 1 second? I see you have your video on. You're coming in a little choppy. Do you mind turning off your video? Then maybe you can come in a little bit clearer. Hopefully that'll save some bandwidth.
Is that better? Yeah, hopefully. Yeah.
Oh, that sounds better already. Thank you.
So for the wonderful. So for the concrete sampling and testing, we sampled in accordance to ACMC 42, and we collected about 92 cores across the entire north approach, where one core could be utilized for multiple tests since these were going to be pretty large cores. We performed about 625 tests total, and we decided on collecting the cores in the most critical concrete sections, for both vertical cores and horizontal cores. And I'll explain a little bit of what that means in the next slide. So the field sampling, again, we collected vertical cores and horizontal cores, as you can see on the top right sketch. We collected the cores within the theoretical load path, since these were, again, the most critical locations of the pile caps. We collected in two directions to confirm the isotropic nature of the concrete, making sure that the mechanical properties were equivalent in all directions. And again, as you can see, these were pretty long cores, so we could use one single core for different tests. And so the bottom sketch shows how these tests were sort of divided. For some of the pile caps, since the height of these pile caps were up to 10 feet, as you can see on the right, some of these cores were pretty long and weighed over 200 pounds. So this was quite an effort to be able to collect these cores. Next slide, please. So this is the entire lab testing matrix for all of the pile caps with all the different tests that we performed. And as you can see here, it's a pretty extensive program, which for an effort like this, it does take a village to be able to perform such studies. So we did this investigation in coordination with Tony Manzella and Mike Mazzulla from Pannoni for the coring, a portion of the material testing, and Carla Sanshore from WJ for the petrography. It does take a village to pull something like this, for sure. Next slide, please. All right, so for the mechanical properties, again, we did compressive strength based on ACMC 39, split tensile based on ACMC 496, and modules of elasticity and stiffness damage testing, where naturally the internal microcracking from these types of cracking and expansion can result in worsening mechanical properties. So we wanted to make sure that we were testing for those for the repair design. Pretty straightforward. Average compressive strengths, the tensile, modulus of elasticity, and stiff damage testing were reported, where the values in parentheses in bold, where some of the limits based on the design values for the original designs. So as you can see, strength was pretty okay. A handful of lower split tensile locations, but in general, fairly low modulus of elasticity in general. So I'm sure that Nick could probably tell you that all of these were used to make sure that the design was appropriate for these mechanical properties of the concrete. For the petrographic testing, the petro was performed following ACMC 856, where we were looking at the composition, aggregate types, water to cement ratio, SDMs, any presence of deleterious reactions, and cracking and overall condition, as well as for hardened air void testing for ASTM 457 and the ASR damage rate index. And we'll go over a little bit of what that means here in the next few slides. So these are some of the nice photographs that we can get from photography. Again, the best way to be able to fully determine that a concrete has ASR is through petrographic tests. So you can see here some examples of how the cracking starts within the aggregate, around the aggregate, and can create severe damage and cracking to the entire concrete. In general, for the petrographic testing, it was determined that 4 different concrete mixes were used across the north approach, where some piers have fly ash. The fly ash ones, we'll see here in a minute how fly ash has been now known to mitigate ASR. And so, maybe at the time it was somewhat of a mistake to have fly ash in some of these piers, but it's being good in the long term. So fly ash and SEMs are generally pretty good at mitigating ASR, as we now know. Likely ASR induced deterioration, and that was also characterized again by this damage rating index, and then also observed were secondary etrogite present, but not necessarily conclusive of the presence of delayed etrogite formation, which is another whole sort of can of worms that could contribute to severe expansion of the concrete. Next slide, please. So in order to further characterize the ASR, we also performed this calculation of a DRI value. DRI is a unitless scale which allows an approximation of the extent of damage within a concrete sample. It's calculated by counting the number of occurrences or features in a 1 centimeter grid, and then normalizing it to determine a number per 100 square centimeters multiplied by a weight factor depending on the type of feature. And then this is summed up to reach a final DRI value. So this is a process, again, to further characterize ASR based on specific features such as cracking in and around the aggregate, that kind of stuff, of a concrete. So for the petrographic testing, again, the results per pile cap include the cracking condition, which is generally a visual observation and conclusion comes from the petrographer, the DRI value, which we just talked about, air content, and then generally the mix type within these pile caps. As you can see, For the mixed type, for the type 3 fly ash, you can kind of see how these are also showing cracking condition on a minimal scale. So again, further evidence that the use of SDM can mitigate damage from ASR. We also performed residual water-soluble alkali content. Again, it's another one of the ingredients for ASR. So understanding how much alkalis were left in the system helped the advanced models for remaining ASR expansion, where the primary component, again, the alkalis in the cement paste, which are sodium and potassium and hydroxide. The alkalis were tested using hot water extraction and evaluated on a Na2O equivalent basis, where the resulting measurement only provided water-soluble alkalis, which can be as little as 40% of the total alkali content of concrete. Again, it's one of the limitations of the tester. Result of the water-soluble alkali content, again, pretty straightforward. And this is one of the parameters that Dr. Sanchez used in his model. And finally, for the ASR expansion testing, this testing was used to evaluate the residual expansion of the reaction. In this case, we did two different environmental conditions, so one at 100% relative humidity and one in sodium hydroxide solution. And we did this both the standard and accelerated testing, one at 38 degrees C and the other one at 60 degrees C. Next slide, please. These are some of the results of the 4 different combinations of the ASR expansion testing. In general, we perform some of the accelerated tests primarily to start collecting data in a shorter period of time versus the long-term testing, which does take about a year. As you can see, though, the 60 degrees C and sodium hydroxide solution, in general, the sodium hydroxide solution for both resulted in extensive is average percent expansion. I believe these results were primarily used qualitatively to evaluate the severity of the ASR in these concretes. But at the same time, I do believe that Dr. Sanchez used primarily the 38 degrees C with the sodium hydroxide solution for his models. Next slide, please. Alrighty, so to recap again, this was a fairly extensive material testing investigation of all of the different pile caps of the north approach, where all of this information was taken into account again to be able to provide information for both the model for remaining expansion, ASR expansion, as well as to verify some of these mechanical properties for the repair encapsulation for Nick and his team. Next slide, please. Yep, and with that, I believe that we'll go over the encapsulation now. Nick.
Further repairs, rehabilitation based on the findings. We had little guidance. Basically from Federal Highways, we had this 2010 report. It basically concluded, as previously stated, you must have alkalis and silica within the concrete and aggregate, but you also must have moisture in order to sustain the reactions. Our initial thoughts were that the reactory moisture was coming from basically ambient sources, is down within a high water table, and there are many ways for moisture to continue to enter the footing. concrete substrate. As the cracking advances, there's even more opportunity for moisture to continue. But as we went through the research, both with Dr. Sanchez and Dr. Folliard out of University of Texas, their research showed that the moisture contained in the initial hydration of the concrete was sufficient to sustain ASR reactions throughout the life cycle of the concrete. This turned our design philosophy away from preventing moisture to some way preventing the expansion of ASR. Other key findings from the literature and the what has been done. Initially, we had hoped that lithium would be a mitigation. We quickly found that this did little to prevent the further expansion. We tried breathable sealants that would basically prevent moisture from coming in, but allow the excess to continue. We tried this, and then again, through this testing that BDI did, we saw that the expansion was continuing to occur. So based upon the previous study, we turned to an encasement or encapsulation method, where basically we would restrain such expansion due to ASR by confining the core load path within the footing. This is an example that was done in South Africa on a similar footing, where you see both the mat and the post-tension footing as an end result. So our conceptual concept was to do something similar. First, we had to do a detailed inspection to determine the amount of damaged concrete. That inspection would require that we expose the entire footing. Some are currently exposed. Some would require us to excavate around the entire footing. And because the bottom of the footing had never been inspected, or there was no, except through our coring, any evidence of the level of impact of that concrete, we needed to have access to the bottom of the footing as well. The footing is supported on piles, so our conceptual and final design included excavating underneath the footing so that it can be inspected and damaged concrete could be removed. Based on the test results as provided, we then took those major mechanical properties of the existing footing and put those into models that allowed us to have some predictive fashion of what design values and what we need to do to actually encapsulate, both with the concrete as well with the post-tensioning, so that we could stop the expansion progression of the footings. We then decided that after all was done, we would continue to monitor through structural health monitoring, basically on the post-tensioning, to see if our theory or validate our theories, and to be able to react on whether, if we weren't accurate, provide additional post-tensioning or other methods to, again, slow the progress of the expansion and therefore the deterioration of the footing. So our northern approach was our first effort for mitigation. Some 18 actual footings, again, some exposed, but mostly not exposed, buried beneath the ground. We decided to encapsulate these footings with high performance fiber reinforced concrete and then post tension after the encapsulation had cured. The sequence for the ASR rehabbing was after there was the excavation, and you see the extensive excavation. We would then inspect the entire footing with an MBIS inspector, defining the deteriorated or damaged concrete for removal. That removal consisted of basically either hydro or mechanical means to remove some 5 inches of concrete around the entire footing. Based on just construction methods, we've also looked at and see if any of the precast piles were damaged. We would do substructure repairs in accordance with VDOT standards on them as well. In the anchorage zones, those zones which maintain the hook and tie efforts, we wanted to remove all the contaminated concrete. So we looked at methods of sequential and phased removal of that concrete while we maintain the load path and load bearing capacity of each footing as we remove and replace the concrete with high performance, again, fiber reinforced concrete. Our goal was to do the encapsulation in 2 placements, the bottom slab and then the walls and top slabs. So there was also a mass concrete concern and heat generation due to that on both the existing concrete substrate as well as the placement. Again, this was fiber reinforced concrete that we're replacing. So there were a number of, I'll call it, challenges of developing this mix design for the concrete, because while you wanted it to be impermeable, you also needed the flowability, a self-consolidating effort of the concrete in order to make sure that it covered all these substrate areas up to 2 feet for the encapsulation. So let me go through some of the major challenges. Again, from the data that we obtained from the testing, we did a bunch of computer models using LOSA for first the main span, as well as a soil spring model for the entire structure. We then broke down and did another LOSA model for the northern approaches to basically be able to predict the in-service behavior due to the damaged concrete and the structural properties of that concrete. We then applied Lucas for a local finite element model as we started to determine what type of encapsulation and reinforcement is needed. And again, to maintain the strut and tie mechanism of the footing as we replace the anchorage zone concrete, we did that analysis as well. Because of the additional loading of the encapsulation, we also redid our pile cap analysis to make sure that we didn't overstress the piles. And of course, we had to make it exciting because that additional load did take the piles to their limits. So we went back, looked at the actual construction piles, loadings, to make sure that we did have the capacity once we did put on this additional weight of the encapsulation. The other challenge was to develop a mix that can meet all the needs. Working with the Virginia Transportation Research Council, we developed 3 separate fiber reinforced ultimate high performance concrete and high performance concrete mixes, which were tested in the VRTC labs, where we were looking for different properties to give a go for that mix. For the anchorage zone, we depended on our splint tensile strength of the control mix to make sure it was feasible. For the wall or encapsulation, we're looking more at permeability, as well as flowability at the slab mixes. All of these were in a controlled lab. We worked with our admixture vendors as well as suppliers, which was another challenge, because in this area of the James River, Varina Enon Bridge, there were not a lot of suppliers that could, one, meet the capabilities of these mixed designs, but 2, have the production capacity to provide ready mix volumes such that we would not develop cold joints in our wall or slab footings. This was very important in the pre-award analysis of constructability, but we were able to find 2 options at pre-bid, 1 supplier that could do it, or we could have mobile mix on site that was able to meet our needs. And finally, it was the post-tensioning. We decided to go with PT bars versus strand tendons for providing the post-tensioning. We felt this was more, again, constructible and more readily monitored than going with tendons or strands over the long run. Those cores that the post-tension bars would go through would be another challenge, given the huge dimensions of the footings. As previously shown, the cores can be very extensive, and they had to basically be able to support the straight bars once they were completed. Here is just a snapshot of the post-tensioning layout and design, where we see in the elevation views how they are arrayed to provide the compressive forces to basically stop the progression and expansion of the ASR. Again, it was our conclusions that the chemical reaction and mechanism would always be there for ASR, but through research, if we can apply some 5 megapascals of counteracting pressure, we can stop the expansion progression. And Dr. Sanchez basically developed his models based on that, and that went into our post-tensioning strengths and needs in the final design. Currently, the project has been advertised. We had 7 bidders, and the low bidder, Fresnet, was able to be within 2% of the engineer's estimate. So we were very pleased with those results. The contract has now been awarded. We've been through the review and shop drawing phase, and we hope to start excavation and production probably within the next 30 days. So that's where we are with the project. Marisol and I would be happy to take questions at this time.
All right. Thanks, Nick. Thanks, Marisol. Actually, I have I guess, a question first here. Yes, if anybody has a question, please use the Q&A function to get it in, and I'll read it for you. First question, I guess, for me was, for that the encapsulation, is is there any standards or specifications on any a minimum thickness around that, or is that more just per your design? And then, I saw in the detail there was a waterproofing. Are you trying to avoid bonding the existing concrete with the new concrete, or I saw that you did do some hydro demolition for that? I guess I was looking at, would you roughen the surface to get a better bond, or is that waterproofing kind of preventing that?
The waterproofing is more a bonding agent. As I mentioned, and I will highlight, we were concerned about the bonding between the existing concrete substrate and the new concrete. The biggest concern was that the heat that would generate would act as a debonding agent. So we wanted to make sure that the differential between the two surfaces, and there's a spec that we included, that there had to be a coupler that we made sure it really isn't a waterproofing per se anymore. It's more a bonding agent. If it still showed a waterproofing, then that is an old slide, I should say, because as we went along, we basically, the sealant or waterproofing the existing substrate took third place to the fact that we really wanted a good bond between the substrate and the new concrete. Your second question was on the thickness. Your first question, rather, was on the thickness of the encapsulation. That was based on our models and what was needed. I guess the fine difference between what it was needed to confine the ASR expansion and the additional weight posed on the piles due to the encapsulation system. As I said, we were teetering on the limits of the pile capacity based on current LLFD codes and what we needed to have sufficient forces to counteract the further expansion of ASR over time. Again, what we found through the research and Dr. Sanchez, that over time, the phenomena of expansion would continue in perpetuity and continue to deteriorate the concrete substrate unless there was a pressure that basically stopped that gel from expansion. That pressure through research is 5 megapascals or 7,000 psi. So we're looking to exert that through the encapsulation system, both the concrete and the post-tensioning system.
Gotcha. I'll open it up. If anybody has a questions, put it in the chat or the QA function there. I guess I have another one here. When you said you excavated under the pile, was there any concern of settlement from the excavation? I guess in the research, I guess they touched on that previously, but is there any concern now that you have to go under the cap?
No, that question was asked a lot initially during the design phase and then the bid phase by contractors. The footings are supported on piles, not the soil underneath. So as long as the piles, the pile group were functioning, and we had no reason to think that they aren't, because there's no evidence of settlement over the 30 years that the bridge has been in service. We were confident that there would be no settlement or movement of the footing once you remove the soil from underneath the footing, because again, the soil is not there to support the footing. The footing is supported on piles.
Yeah, I was talking more of the soil underneath. So once you did excavate, that would create, I guess, a void between your encasement and then the soil below. Was there anything special in the specification?
I'm sorry if that was your question, and I didn't show it in the slide presented here, but there is a mudslide backfill that that once we had inspected, removed the bad concrete and reformed the encapsulation, there would be a mud slab up to the bottom of the encapsulation for future support.
Okay.
Flowable fill would be placed back in that voided area. I'm sorry. That's exactly what it is. I just didn't show the backfill slides.
No problem. Right. Any other questions? Oh, yes, I got one here. So what is the expected design life of the encapsulation? Is VDOT hopeful that the encapsulation will make the design life of the substructure to match the remaining life of the rest of the bridge?
Yes, that is exactly what the goal is. That the mitigation effort, ASR mitigation efforts through the encapsulation with the post-tensioning will now extend the life of those footings such that they align with the service life of the 100-year design life structure of the Varina Enon Bridge, which 75 more years. Now, as I said, one of our titles on that is that we will have structural health monitoring to see if the expansion continues, and there are mechanisms to either increase the post-tensioning or take other measures to further mitigate, to further extend the life. Should our assumptions, should all our calculations not be as predictive as we hope they will be.
Great. I have a follow-up to my previous question there is, how difficult was installing bottom of the pile cap dowels and new reinforcing steel for encapsulation?
We will see that in the next 3 months.
Right.
The contractor hasn't actually installed it. He has submitted a sequence of construction for installing that. And he seems to feel very confident that it can be done within a means that is productive and meets their financial models. But the proof is always in the actual construction out at the site. And we anticipate that to start occurring again this spring. So give me a call, say in August, and I could give you how it's actually going.
See who drew the short straw to crawl under there?
Yeah.
Great. I think I have another question. How was the stiffness damage testing used to implement the retrofit?
Basically, all of those, it was used to basically predict the life and the service life and how much remaining expansion remains in the footing. In each particular footing, it varies from, as was stated, the minimal impact to severe. The SDI was used to help us determine how much remaining potential expansion could occur. That being our worst case for design of the encapsulation and post-tensioning efforts.
All right. Give it a second. I don't see anything else. So, all right. Well, That was a great presentation, Nick Marisol. Thank you so much for presenting to our group. We really appreciate it. I will take over the
Turn it back to
screen.
you.
Yep.
Yes.
Here we go. So on behalf of SEI, we do thank you very much. I will reach out to you separately. We'll get your address, and we would like to send you our fancy SEI Philly Yeti mugs. So again, thank you very much. I'm also in the QA chat for everybody on the call, and as yourselves. There is a link to the PDH, and if you choose, you want to take out your phone and scan the QR code here, and that will take you to a link to download the PDF, and then you can fill out your name and have that as a PDH. So I will leave this up for a minute. And again, thank you so much for presenting. We appreciate that. And everybody, to our members, look out for our April ASC Multi-Tech. It'll actually be advertised through ASCE, or you can register through ASCE. However, we will send out some links for you to get that. So be on the look at that. It's April 14th. It's a Tuesday at Swarthmore. It'll be a good time. We'll be presenting our scholarships to the students, the winners of the student winners for the scholarships. That money came from our golf outing last year. And so again, that's why this golf outing is very important for us. A lot of the money does come from our sponsorships. So go be on the lookout for the link for the golf registration. Encourage your companies to donate or to become a sponsor for this golf outing, because it does go to the students, it does go to the kids, that will eventually become our peers. However we can help them. That's why we're here. That's why we do these organizations, to help them and grow our community. Moving forward. So again, thank you very much, Marisol and Nick, and thank you everybody else for attending. Have a great rest of your day, and have a good weekend. Enjoy this weather if you're in the Philly area, and go Orioles. Nobody cares about the Phillies.
Go
I guess I
Nats.
shouldn't say that as SEI Philly. I guess go Phillies.
Yeah, thank you.
Take care, everyone.
Take it easy.